Here is section 7.7, problem solving for functions. How can you use functions to analyze situations, draw conclusions, or make predictions? This is an extra credit section, good for some bonus learning of putting together thoughts that you already know, and just putting them together in a new and more powerful way. Let's get started. You have a worksheet to go along with this, so any problems that I do on here that are on your worksheet, you need to make sure to fill in. The graphs represent ticket sales for 3 upcoming games, with X representing time and Y the rate of ticket sales. Which game will be the easiest for your cousin to plan how many hot dog buns to buy? Which would make it the most challenging? So each of these graphs basically represents time and rate of ticket sales. So as time goes on at the baseball game, ticket sales are, in this one, they're going to go down because at the beginning of the game, you have the most sales. Toward the end of the game, nobody's coming in. Okay? This one has the same amount of people coming the whole time. So no matter what inning, let's say you've got 30 people coming into the game every inning. This one's unpredictable. Okay, people come a little bit late, and then sales really drop, but then toward the end of the game, sales go up again. So which one is going to be the easiest for your cousin to plan how many hot dog buns to buy? That would probably be graph A or B. In my opinion, graph A would be pretty easy to predict because you know how many people are there at the beginning. And so they're going to typically be there for the whole game. And so it would be easy to kind of predict that. Graph B has about the same amount of people coming in every time. So again, you could predict how many people are going to be there. So I would take A or B, whatever reasoning you give me, as long as it's good. I would believe graph C is going to be the most challenging because you don't know exactly how many people are coming in. It's really hard to predict. So graph C is definitely the most challenging. Here we're going to graph a model rocket. It's going to rise up really quickly, but then it's going to slow to a stop as it reaches its maximum height. So there we have this. Rises quickly, slows to a stop as its fuel burns out, right? That's how model rockets work. They go up until their fuel runs out, and then it begins to fall quickly, so its height is going to go down real quickly. But then a parachute is going to open. And after the parachute opens, it's going to fall gently back down. So the parachute is going to slow its fall. So its height is going to go down gradually. There is a graph of that situation. Here is when it's zooming up. It's slowing down. It's about to run out of fuel. Uh-oh, it ran out of fuel. It's falling quickly. Parachute opens, and bam, it coasts and slowly goes toward the ground. And that is a graph of that situation. This one is a got it. You walk home from school, stopping at a friend's house on the way. Sketch a graph to describe the total distance you walked during the time you walked home. Here's the difference. I want the total distance you walked during the time you walked home. So if it's total distance, it's not like those other graphs we've done. The other graphs were distance from home. So let's say you walk home from school. So here at time 0, you're at school. And you haven't walked at all. Okay, so if you're at school, we can't walk home from Meigs Middle School, but there's lots of schools where people walk home. Okay, let's say that you're at home or you're at school. You haven't walked at all, but you're going to start walking home. So your distance is going to go up. At some point, you stop at a friend's house, so your distance doesn't change. You're there for a while, and then you're going to walk home from school. So we're going to end up here, maybe. And then you're going to stay at home. So this would be your home. This would be your friends. And so your distance, you walked to your friend's house, stayed at your friend's house, so your distance didn't change. Then you had to walk some more. You had to walk home. And then you're at home, your distance doesn't change. So that would be one graph. Your graph could really look like anything. Maybe your friend lives real close. Maybe you were only at your friend's for a little bit, and then you had to walk home really far home. Okay, maybe you mostly walked to your friend's house real fast. You ran to your friend's house. You were there for 5 minutes, and then you slowly walked home. So as long as your graph has 3 parts, with distance increasing at the first and last part and staying the same in the middle, you're good. A little hint that I have for you, because we're switching gears here, we've got to figure out if equations are linear or nonlinear. If we want to look at an equation to do that, there can be no exponent on the x. You might want to jot that down. No exponent on the x. Actually, on any variable. So nonlinear has no exponent on any variable. Let's see what that looks like here. And you can draw the lines or write these out in your notes however you want. There's no exponent. Whoops, I'm in the wrong mode here. No exponent, so it's linear. No exponent looks kind of funny, so it's linear. This has an exponent. It's outside of the parentheses that x is in, so that's nonlinear. This has an exponent on the x. It's nonlinear. No exponent. This is in y equals mx plus b, which is linear. This has an exponent outside of the parentheses with x in the inside. That is nonlinear. Here we have this problem that says complete the table of values for the function. And it's y minus 5 equals 3 times the quantity x minus 1. Let's put in some values for x. And then normally we just come up here into the equation and plug in our x value to get each individual y value. Well, if you notice, it's not set up as a y equals equation. So what you're going to have to do is take x and replace it with the x here. So we've got y minus 5 equals 3. Instead of x, I'm going to put negative 2 minus 1. Then I've got some work to do. I've got to do parentheses first. That gives me negative 3. 3 times negative 3 is negative 9. Bring down your y minus 5. To get y by itself, I'm going to add 5. So then I have y equals negative 9 plus 5 gives me negative 4. That's a lot of work. Every single time you're going to have to plug in for x up here and then solve for y. Let me show you a way to make that a little bit more quick. If you have it set up as a y equals equation, it's going to be a lot faster for you. So if you look here at this equation and then get y by itself, it's y minus 5, so I'm going to add 5, and that gets my equation to be y equals 3 times x minus 1 plus 5. I could even simplify this more. I could distribute and get 3x minus 3 plus 5. And then I combine my like terms to get 3x plus 2. this equation is equivalent to this equation. So instead of using this top one and having to solve a bunch of times, you can just find the values of y using this equation down here. So I'm going to go ahead and rewrite that as y equals 3x plus 2. And then we're going to see that it's going to be a lot easier to find my values of y. All right, if we use this one. Because if x is negative 2, 3 times negative 2 gives me negative 6. Negative 6 plus 2 gives me that negative 4, which is what we got before. Just a little bit easier way to solve that. Let's go ahead and solve all of them times negative 1. And you can just put this in your calculator if you want. 3 times negative 1 plus 2, that's negative 3 plus 2, which is negative 1. Right, if I plug in 0 for x now, okay, if x is 0, 3 times 0 is 0, 0 plus 2 is 2. If I plug in x is 1, 3 times 1 is 3, 3 plus 2 is 5. If I plug in 2, 3 times 2 is 6, 6 plus 2 is 8. So there we have all of the points found using this equation instead of this complicated one. Okay, we solved for y to get this one. It makes it a lot easier. We can also graph those. So negative 2, negative 4. I'm going to do this quickly because I'm running out of time here. 0, 2, 1, 5, 2, 8. It makes a nice straight line. Y-intercept of 2, slope of 3. So using the points or y-intercept, you've got your line. Let's check out our next problem. We've got to complete the table of values for the function y equals x plus 2 quantity squared minus 1. This one we cannot distribute and simplify because we don't know how to do that. That's an algebra skill. So we've just got to plug in. And I'll do this real quick, again, running out of time here on my video. So y equals x is negative 2. That's the only thing I'm going to change. So I do what's in parentheses first, and I get negative 2 plus 2 is 0. 0 to the second power is 0 times 0, which is 0. 0 minus 1 is negative 1. Okay, it's time to plug in. Instead of x being negative 1, I'm going to plug in, or I'm sorry, negative 2, I'm going to plug in negative 1. Negative 1 plus 2 gives me negative 1 squared minus 1. Negative 1 squared is negative 1 times negative 1, which is positive 1. 1 minus 1 is 0. I'm going to plug in 0 now. 0 plus 2 is 2, so I have 2 to the second power minus 1. That's 4 minus 1, which is 3. I'm going to plug in 1 now. 1 plus 2 is 3. 3 to the second power is 9. 9 minus 1 is 8. You can type this all in your calculator if you're having trouble keeping up. 2 plus 2 is 4. 4 to the second power is 16. Minus 1 is 15. And we can go ahead and plot those points. Negative 2, negative 1. Negative 1, 0. 0, 3. Ooh, this is not linear. Remember, it's because we've got that exponent of 2. 1, 8, and then 2, 15 is going to be up here. So this looks like that. So we have found points, and we have graphed it, and we can see they're not linear. If we were to graph more points on that same line that I just drew in green, okay, it looks like this. That is called a parabola. You will want to remember that word. It will be worth some extra credit on your test. All right, good luck on the homework. Take your time. You'll do great.